great honor to welcome you to the 26th Annual Presidential Lecture. First, I want to say again thank you to our wonderful entertainment today. Please help me thank Maurita Mead and Sherry Rhodes for that beautiful musical prelude. What a great way to start the afternoon. Thank you. You have set the tone for an engaging and inspiring lecture, and I know we're about to have that. It's especially wonderful to enjoy the talents of our School of Music faculty this year. You show us that despite the challenges the school faces due to the flood, you continue to develop your extraordinary talents and to share them generously with your students and with our community. You are an inspiration to us all, and we look forward to new facilities in the not-too-distant future. Thank you. As many of you in this room know, President James O. Friedman established the Presidential Lecture Series over a quarter-century ago. This event not only showcases some of our many outstanding faculty members, but it also serves to encourage communication across disciplinary boundaries. And I can tell, just from looking at the audience today, that there are many people here from many different disciplines this afternoon. As well, the lecture brings the tremendous work of our faculty scholars to the general public. What better way to do it than in a venue like this one? For 26 years, through this forum, we have proudly shared our excellence in areas ranging from mathematics to literature to the health sciences to law, and today, physics and the physical sciences. I'm pleased to introduce to you our 26th presidential lecturer, Don Gurnett, the James A. Van Allen and Roy J. Carver Professor of Physics. Don Gurnett is a true Iowa treasure. He began his affiliation with the University of Iowa in 1958 as an undergraduate working in James Van Allen's Space Research Group. But his destiny as one of Iowa's great scientists actually began long before that. As Professor Gurnett himself has said in interviews, he had already gained a kind of acclaim as a youngster. He'd been a national champion model airplane flyer as a high school student in Fairfax, Iowa. He came to the University of Iowa as an engineering student with an interest in airplanes, electronics, and rockets. At about this time, the Russians had launched Sputnik, some that many of you in this room remember. I certainly remember it myself. Don saw history being made, world history and his own, when he watched that satellite fly overhead. When the United States launched Explorer 1 shortly after, University of Iowa undergraduate Don Gurnett walked over to Physics Hall to, as he says, see if they needed help. Flight wasn't the only thing that sparked Don's imagination. It wasn't long before his high school model rocketry led him as an undergraduate to designing a very low-frequency radio receiver for Engine 2. What finally pushed him into physics as a career was hearing sounds from space that the receiver sent back to Earth. You can see from Don's biography in your program that in the 50 years since, he's built an internationally renowned, award-winning career from those young enthusiasms over the possibilities of flight and the sounds of space. That career has led him to groundbreaking research, innovative teaching of our students at the University of Iowa and well beyond, and even a major artistic collection. His collected space sounds formed the basis of Sun Rings by composer Terry Riley, which was premiered here at the University of Iowa at Hancher Auditorium by the Kronos Quartet and has since then been performed around the world ever since. Don has said that everything he does, even when he dabbles in the music world, is rooted in the basic quest for knowledge that drives everyone in the academic world. His first and his last question is always, so how does it work? That's the question he asks of his subject matter every day, and it's the question he pushes his students to ask and to pursue to the final answer, and maybe even beyond. That's how new knowledge is created, how literally the mysteries of the universe are solved. One of Don Gurnett's nationally known colleagues is Margaret Kivelson of the Institute of Geophysics and Planetary Physics at UCLA. When asked to provide some thoughts about Professor Gurnett and his work, this is what Professor Kivelson shared with us. This is a quote. "Space plasmas keep no secrets from Don Gurnett. A brilliant sleuth with finely honed skills, he is able to interpret colorful dynamic spectrograms of plasma wave power in a truly Holmesian manner, deducing from his data how, where, and why the fingerprints are formed. One can almost believe that his highly intuitive skills will one day be used to read the past and future from the sounds of space." We are so very fortunate that Don Gurnett has been listening to and reading the sounds of space and much more here at the University of Iowa for his entire educational training and his professional career. He's mentored and inspired generations of students and colleagues, and he's moved scientific frontiers forward in truly, truly remarkable ways. I am absolutely honored and privileged to introduce him today as this year's presidential lecturer, Professor Don Gurnett.
Thank you. Thank you very much. You did some research. Thank you very much, President Mason, for the long introduction. You obviously had somebody researching my early career here. And okay, my talk today, I hope to take you on a tour from the beginning of the space age, as I saw it, which was over 50 years ago. It's hard for me to actually believe the 50 years have gone by. And I will start this discussion by discussing the International Geophysical Year in 1957. This was in my mind, a famous and absolutely crucial year in my life, and it was also for the country. Now, in the early 1950s, there was an International Council of Scientific Unions convened a series of international geophysical studies. They wanted to basically study worldwide phenomena like climate, oceans, and things like that. And this year, International Geophysical Year was set for July 1957 to July 1958. Now, both the United States and the Soviet Union proposed to launch an artificial satellite as part of that activity. The idea was a satellite could, scan the entire Earth. At that time, the idea of an artificial satellite was theory. It had never been achieved. You have to get an orbital velocity of 18,600 miles an hour to get an object in orbit. And that was, at best at that time, thought to be just barely possible. Now, Professor Van Allen, who was my mentor and later colleague for 50 years, he was very active in promoting a U.S. satellite as part of the IGY. And his work, earlier work, which is covered in a very nice book here by Abigail Forstner. I'm giving you an advertisement for her book here. If you want to follow the details of Van Allen's early career and his work with Wernher von Braun with the V2 rocket, that's an excellent source. Now, the official U.S. satellite project at the time was called Vanguard. Now, the reason it was I call it official here, there was another hidden project by Wernher von Braun. He was prohibited from trying to launch a satellite because of political considerations. Von Braun, a German rocket scientist, very famous for the later Apollo missions, he was at the Redstone Arsenal, which is now Marshall Space Flight Center in Huntsville, Alabama, and he was developing a intermediate range ballistic missile called Redstone. And President Eisenhower at the time did not think it would be a good idea to try to use an intermediate range ballistic missile to launch a satellite. So he commissioned this development of a civilian spacecraft and rocket called Vanguard. Curiously enough, it was developed by the Office of Naval Research, but it had no military intent. Now, what was I doing in 1957? Sally, you've stolen some of my thunder. I graduated from a small high school in Fairfax, Iowa in May of 1957, so that was the year I graduated. There were 7 in my graduating class and 2 in the class after that. It was a one-room high school run by a nun who I kept track of my entire career. I'd have to say I got a very good education there. They did not teach physics in high school, but I later learned that. As you said, I was heavily involved in model airplanes from a very early age, and that turned out to be a crucial thing in my life. There was a very active club up there with people from Collins Radio in particular, adults, and they were mentors. And they took us to model contests and all that kind of thing. And being from Collins Radio, they were also interested in developing radio control models. Nowadays, you can go down to the hobby shop and buy a radio control unit for $100 and plug it in. It works. Back then, they were made out of tubes. I'd almost like to ask how many people even remember tubes here. But that's how we build them. And I built the radio control models with tubes and A batteries and B batteries, and I learned all about electronics in high school doing that, especially from these people at Collins Radio. I also had a significant influence from Dr. Alexander Lippisch, who you may or may not have heard of. He was a German scientist, aircraft developer. Actually, in the aircraft world, he's one of the most famous aircraft developers. He developed the Messerschmitt 163. It was a rocket-powered fighter flown by Germany during the Second World War, and it was the first airplane to fly faster than 1,000 kilometers per hour. And after the war, he was working at Collins Radio, and he headed an aeronautical development group up there. And believe it or not, our model airplane club used to meet out on the Cedar Rapids Airport, right out there by the main runway, and we would fly airplanes out there. When I leave from Cedar Rapids, I often think I used to be flying model airplanes right out there. And Lippisch would come out and visit us. And he didn't use wind tunnels. He used model airplanes for developing full-scale aircraft. So he was out there coaching us to design this type of airplane, that type of airplane, and so forth. He was known as the father of the Delta wing, the Concorde, which has a delta-shaped wing. So he had us building delta-shaped wings out there and flying them. And being a rocket scientist, and since he developed a rocket-powered airplane, I tried to do that too. And I started working on building rockets out of saltpeter, charcoal, and sulfur. I remember very vividly going into a druggist at Cedar Rapids where I often bought this stuff, and he said, son, what are you doing with that stuff? And I told him I was making rockets, and he said, have fun. Anyway, after all that, I wanted to be an aeronautical engineer at one point, but the electronic stuff got the better of me. And I was working at a hobby shop up at Cedar Rapids. I worked there for 4 years, and I was practically running the model airplane side of the thing. And when it came to decide where to go to school, I decided the University of Iowa. That's because I was working in Cedar Rapids and I needed the money. And so I arrived here on about September 20th, and I was here all of 2 weeks, and Sputnik 1 was launched. And this was really an eye-opening event for the United States. I'm curious, how many people here were watching TV when Sputnik 1 was launched? Quite a number. I hope you will attest that had a real impact on the country, because we were in the middle of the Cold War, and we had a Russian object flying overhead, and that meant the Russians were capable of building intercontinental ballistic missiles. And this changed the entire country, because since the United States was then perceived as being behind in technology, there was a big infusion of money into education, especially in the science and engineering fields. In fact, our building over there, Van Allen Hall, was funded eventually by NASA. It's paid for by the government, and that was how it happened. Now, Sputnik was about 2 feet in diameter, twice the size of a basketball, weighed 183 pounds. Just to show that the Russians could really launch things into space, 1 month later they launched Sputnik 2. It weighed 1,120 pounds. And it carried a dog, Laika, the first living thing in space. Unfortunately, they had no way to bring it back alive. Now, let me go on to the Vanguard program. Here's Vanguard. Picture of this satellite, weighed 3.1 pounds. Contrast that to the Soviet Union's Sputnik spacecraft. About the size of a grapefruit, about 6 inches in diameter. And here's a picture of the rocket, which, as I said, was developed by the Naval Research Lab. And I remember this vividly because on December 6th, there was a widely publicized attempt for the United States to catch up and launch the first spacecraft. I see a lot of heads nodding out there. You probably know what happens. Here's the picture of the launch of Vanguard, and I'll start it here. Classified. Right. I wanted to show you this picture so that you'll have an idea what can happen if you go into this line of research. At that time, Professor Van Allen was working with Wernher von Braun down at Huntsville at the Redstone Arsenal to develop the spacecraft that von Braun was keeping in apparently a secret location. I'm not sure it's secret, but the government didn't know about it. You can read the book. Read one. I have a book at home about von Braun by Neumann. It's really interesting reading. He had the foresight to think that they might need him. And he developed that Redstone rocket into what was now called the Jupiter C. And it had several stages. I can't go into the details, but there was a spin platform on the top that spun the final stage like a football, and it was programmed to lift off, go up in the air, finally go horizontal, and then they fired a whole group of small solid propellant rockets to get the spacecraft up to 18,600 miles an hour. Van Allen he was interested in cosmic rays, and there is a latitudinal gradient in cosmic rays, which you can see on the ground. There's some very curious altitude effects that he wanted to study. And so he provided, with George Ledwick from Tiffin, Iowa, that was the engineer involved, just the two of them essentially. They provided a Geiger tube here, which was mounted in the spacecraft, and the Jet Propulsion Laboratory built the transmitter and some of the other electronics. And it was launched on February 1st, 1958.
5, 4, 3, 2, 1. Fire command. Fire command.
We had a little celebration out at the Hoover Library last year, the 50th anniversary of this launch. And this is an iconic picture taken in the National Academy of Science building and shows Bill Pickering. He was the head of the Jet Propulsion Laboratory, James Van Allen here, and Wernher von Braun, celebrating the success of Explorer 1. They must have been reasonably confident because they flew from the Cape up there before the launch so that they could have this press conference if the spacecraft came around in the first orbit. And shortly thereafter, Van Allen made a tremendous discovery, which is that the Earth is surrounded by intense radiation belts, two such belts, an inner and outer belt as it was called, and that was totally unexpected. What happens is a charged particle, if you just take a physics course, you'll find out if there's a magnetic field here and you shoot a particle in there, a charged particle, it'll orbit around the magnetic field, and it will also bounce back and forth between two mirror points, and it'll do that essentially forever. This possibility was actually known by a German scientist who published it years earlier, Sturmer. But they never thought there'd be any particles there. Why should there be extremely energetic, up to million electron volts, particles moving almost the speed of light? And the intensities were so high that it was dangerous for a human being to fly here. Fly through that region. You can survive it, but you don't want to spend much time there. The shuttle and the space station, for example, flies at a very low altitude under this main radiation belt. Now, I was taking classes over in the engineering building, which is the same place it is now. And at that time, the physics building was now McLean Hall, right across the street. And this was, of course, in the news. Van Allen's picture was on the front page of Time magazine, and I just couldn't stand it. I had to go over and see. You put it, if I could help him. That wasn't. Was that a quote? I hope I didn't ever say that. Probably did. But anyway, I went over there to see if I could get a job, and I didn't see him the first time there. I saw his secretary, Agnes McLaughlin, who later became a lifetime friend. She died about 2 years ago. And she had me write down on a piece of paper what my qualifications were. And I said something like radio control electronics. Excuse me a second here. And that was on the basis of this work I did with the radio control model airplanes. And that was in spring of '58, about April 1958, just a couple of months after the launch of, maybe even a month. And I was also looking for a summer job too, and I applied at Collins Radio. And about a month later, I got a handwritten note from Professor Van Allen inviting me to work in his group. Unfortunately, I'd already accepted a position at Collins Radio, so I ended up working at Collins that summer. I went to see him, and he was very gracious and said, "Come back in the fall, and we'll fix you up with something." So in the fall, he had me start working on a project that was called S-46. The 46 is a proposal number. It has nothing to do with the sequence in which the satellites were being built. And he had me start working with a graduate student, John Freeman, who was developing a detector for this spacecraft. It was called a cadmium sulfide detector. It's essentially the photosensor you use in a light meter. And of course the idea wasn't to detect light, but if you expose it to radiation, it can also detect radiation, especially low energy particles. So I worked with Freeman for a couple, 3 months on that, but gee, being there, it was like a kid in a candy store, you know. There are all these other things, and I got talking with other engineers, and I started working with flip-flops, with transistors. See, I just worked with tubes before. Now we had transistors. They had just come on the market very, very shortly before that. And S-46 rocket failed. My first introduction to space science. The next thing I worked on, Professor Van Allen proposed with now actually a close friend of mine, Frank McDonald, who is at Goddard Space Flight Center, and I still see him at meetings, proposed to fly a series of instruments on a spacecraft that was called S3, and it was to go out quite far from the Earth. And myself and Gene Coulter, he was a senior engineering student. The two of us were selected to work on a digital encoder design. I'd got myself very interested in that kind of thing. And so we started working on that. Unfortunately, about maybe 4 or 5 months into the project, Gene graduated. So I ended up with the encoder design, but I was already very enthusiastic about that. And I want to just tell you a few things here. There were 5 instruments, 3 Geiger tubes and 2 cadmium sulfide detectors, and we had to take counting rates and with a binary counter and shift that data into a shift register and so forth. I mean, it seems simple now, but you know, we had to invent that stuff. This was a NASA project, it turned out. NASA was formed in July of 1958, but NASA had no facilities. They didn't have any buildings anyplace. And so this project actually started at the Naval Research Lab with those same people that were involved in Vanguard. Many of these people later moved to Goddard Space Flight Center, and for years and years I would meet these same people there on projects I worked on. Let me tell you a few things. I've had many trips into Washington, D.C. The Naval Research Lab is just across Washington National, or across the Potomac there, just across from the Potomac. And we lived rather frugally. I thought I would bring out here, I'll put my glasses on to read this, some of my expense accounts. I dug this out. I've got a whole collection of these things in Iowa City. And we flew in there on United Airlines, and here was the price. Round trip ticket to Washington, D.C., $115.60. I was there this trip for an entire week, and my total bill, counting the airfare, was $210. We stayed at the DuPont Plaza, which is a quality hotel in downtown, but we typically stayed several people per room. And my share of that was $7.72. And I see my meal expense here seldom exceeded $5 for the entire day. I'll tell you a few other things here. I'm going to just tell a few stories at this point. Space research had achieved the highest priority you could achieve at that point. If we ordered some piece of electronics, transistors, we got top priority. That's just the bottom line. This extended to other areas. I can remember flying into Washington, D.C. with Jim Van Allen and Kurt Laughlin, and I think it was Bill Whelpley, and we had to take some equipment into the Naval Research Lab, and frankly, we were just running late getting out of the building. So Agnes, Van Allen's secretary, called the Cedar Rapids Airport director of the airport up there. I think I used to know his name, but I can't dredge it out of my memory, and said, please have him hold the flight. Which they did for about 45 minutes, and we went up there, and they let us load the cargo into, there was a DC-6, if I remember right, loaded into the cargo bay. I mean, times were different then. We had to take a radioactive source in there to activate the Geiger tubes. Well, I just put the radioactive source in my briefcase, and we took it in there. Now, this spacecraft was launched successfully. It was called Explorer 1. Curious thing about that, when they started the space program, you can look in this list up here, they started calling every launch Explorer 1, Explorer 2, and so forth, but about half of them failed. So then they changed the policy. They only named the spacecraft after the launch was successful. So this was see that S-46 would have been Explorer 8, I think. Anyway, Explorer 12 made a very important discovery. This is a plot, and I won't go through all the details. This is the radiation intensity, and you see the intensity goes down here, drops very suddenly. The magnetic field is very smooth in here. That's the Earth's magnetic field suddenly becomes very irregular. The cadmium sulfide detector showed a big effect right at that boundary. That turned out to be key data that showed that the Earth's magnetic field here had an outer boundary right around there. It's now called the magnetopause. And the reason that boundary is there is there's a flow of gas, a very high-speed flow of gas that comes out from the sun. It's now called the solar wind. There's a long history of the discovery of the solar wind. For example, if you look at the sun in a solar eclipse, you can see these kind of like streamers coming out. It just gives you the impression there's something going out in the sun. And as early as 1951, Bierman wrote a paper you could see in comets. There's what they call the ion tail, and it was always directed exactly outward from the sun. And there you could see pieces in the ion tail here that would be moving very, very rapidly outward. So this was Explorer 1 showed that there was a boundary here, and that defined a region we could now call the magnetosphere. See, it's the magnetic field of the Earth, but it's like a sphere. You know, it's confined to a not exactly spherical region. It's actually a bullet-shaped region. Later, it was discovered that there's actually a shock wave in this flow. The flow is supersonic, and just like a bullet going through the air, which forms a shock wave out in front of the object here is the magnetic field, there's a shock wave formed out there. Now, I'm going to change the subject now to a whole series of spacecraft, and I will not discuss every one of these, I promise you. These are called the Engine series of satellites, and I worked on every one of those except for Engine 4, and I was at Stanford University working on my PhD at that time. These were the first spacecraft ever launched, built completely at a university. See, these previous things, the Explorers, Explorer 1, Explorer 3, and so forth, they were really Jet Propulsion Laboratory. We provided instrumentation, but here we built the entire spacecraft, and we were the first to do that. And there's no university yet has accomplished as many projects as I show up here. Now, here's the first Engine 1. The name, Van Allen wanted to call it Hawkeye, but there was a classified military project called Hawkeye, so it was given the name Engine. So these three here were funded by the Office of Naval Research, and I might tell you how they were funded. Van Allen just wrote him a letter, a one-page letter, and asked for $100,000. And he also had a little deal that with the Naval Research Lab that they would launch it along with some classified military spacecraft. So I and everybody else working on it, we had to have a security clearance. I had to get that almost from the beginning when I started working on these things. And here's a picture of me with Engine 1. And by now, I was probably the expert on digital data systems. And I designed a very special kind of thing called it was a binary counter, and you put just one voltage on it, and it would change it into a shift register. Kind of a combination counter and shift register thing. That was later the subject of a patent by the Office of Naval Research pursued that. Let's see, what can I tell you about this spacecraft? I remember down at Cape Kennedy, I had, the first digital data system. I'll have to explain that a little bit. All the earlier satellites transmitted data by having a tone that would be transmitted. And I'll have to have another drink of water, I won't get through this talk. They would transmit a tone that would be proportional to the voltage of something you're measuring, like a battery voltage or something like that. And and then they would switch that between various measurements. So if you listen to it, it would kind of go dee 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 as it's switching between various. But that was relatively easy to build. It was terrible to analyze because you had to run it through a special device that would determine the frequency and make a plot on a paper chart, and you had to have students down there measuring this with a ruler. It was really a nightmare. And we had this idea that we should switch to a digital data system, transmit zeros and ones. After all, we kind of started out with digital, with the binary counter and everything, and that's what we did. So this was, as far as I'm aware, the first digital data system ever flown. And I had a guy working for me, Gene Crossett. He later became a minister. He maybe got tired of space research or something and decided to go into a different line of work. But his job was to decode the data. And you play this out on a paper chart, and the pen would go up and down, 0, 1, 1, all that. And he'd have to break it up into 16-bit words and then use a mechanical Frieden calculator to convert the binary number to digital. And that's really a lot of fun. We had no computers then. Computers in our campus did not exist. They barely existed anyplace. And so I can remember being down at Cape Kennedy, climbing on the gantry and all this kind of stuff. And I remember being a little discouraged at the launch because the rocket we were using, a Thor Able Star, about a month later they launched one, and it came down in Cuba and killed a cow and caused an international incident, and we had to reprogram our launch trajectory so that it didn't go over Cuba. We had to go just a little bit east of Cuba. But that was done. I'm sorry, I really like to tell stories. There was another very interesting thing. I remember going to the Launch Readiness Review, which is a review of all the rocket people and the spacecraft people and everything. Are we ready to launch? And they asked us if we would launch with the transmitter on. They wanted that for some tracking purposes. And I remember considering that, and along with Brian O'Brien, I should name some other names here. Brian O'Brien was a scientist that was sort of working with Van Allen. And he was not an engineer, but he was in charge of the scientific instruments. And we decided that although we had done a vacuum test on the transmitter under vacuum conditions, we had not done a test where we purposely lowered the pressure rapidly, as happens when the rocket goes up through the atmosphere. And there's a crucial pressure level. Some of the ham radio people probably know this. There's a crucial pressure which you tend to get arcing. And I was afraid we were going to get the transmitter would arc and blow out the transmitter. So we said no. And so that's the way they launched it. And when it came, launched out of Cape Kennedy, and I watched it go downrange and disappear out of sight. And then you wait an hour and a half to see if it comes over the northern horizon. And they were sending commands from Iowa City here to command the transmitter on. And they reported transmitter came on. And then we got a call from the North American Air Defense Command, who operates the dew-line radar, and they reported they could see 200 objects up there, and they wanted to know what they were. And we didn't know, but just a matter of minutes later, we picked up the signal down at Cape Kennedy. It was called Cape Canaveral at that time, and we decoded the data, and everything looked perfect. And then there was an inquiry into this whole thing. And it turned out the final stage of the rocket, which was also in orbit. And the way that worked, the final stage, we were connected to the rocket, and then there's an explosive bolts that separate it, and there's a spring that pushes the spacecraft away. And turned out when we turned the transmitter was commanded on from Iowa City, the last stage exploded. And the reason it exploded, some investigation some time later, they finally figured out why. A harmonic of our transmitter frequency was on the command destruct frequency. Had we turned the transmitter on the pad for liftoff, and when they armed the command destruct system, it would have blown up on the pad. So there's an interesting story. Here's engine 2. I really have to speed this up now, I know. Engine 2, by then I was the project engineer. I was in charge of the entire spacecraft. This is my spacecraft from the engineering point of view. This is a series of secret naval research satellites. That was Marty Vota, a guy I was very impressed with. He was a manager, he made things get down there in time. For example, if we didn't show up with our spacecraft on the date we were to launch, they had a lead-weighted mock-up they would put in, and we would be left on the ground. That's the kind of way they ran these things. Here they're just about to put the nose cone on the rocket, and that's me standing there, and my job is to make sure they don't do anything bad to our spacecraft. Anyway, I watched this rocket lifted off. It was a night launch, and about a minute or so afterwards, I could see the rocket blinking, and that's because the rocket is going end over end like this, and that's the end of engine 2. So here's engine 3. Incidentally, I should show you the time interval between these is less than a year, and we were working really 60, sometimes even 80 hours a week, as well as going to classes. I can't quite see I did it, and other people. I'm not alone. There's other students working on these projects there, almost all students. And I'm the project engineer in charge of this entire thing. And there's a guy who came to our lab called Roger Gallet, and he played a recording of whistlers produced by lightning, a low-frequency radio signal down in the kilohertz region, and they go like that. And I was intrigued by this, so I went and I built all on my own, essentially, a receiver. And I took it out to my father's farm. You really can't use it around the city here because there's so much 60 hertz power line noise you just can't hear anything. So I took it out in the country, and I heard a few whistlers, and I asked Van Allen if we could put it on the spacecraft. It had a 50-turn loop antenna up there, and because it had analog, and I had to figure out how to transmit the analog together with the digital, and I came up with a scheme for doing that. Van Allen approved it. And that was it. I say it's a turning point in my career. When we launched it, I can remember to this day when we turned the transmitter on, there was just this incredible amount of sounds came out of this receiver, transmitted to the ground so we could hear it. And let me tell you a little bit about whistlers. Whistlers were known before we launched the spacecraft. It was known they were produced by lightning. A guy by the name of Owen Story explained whistlers. They were actually discovered in 1917, and it wasn't until 1952 that an adequate explanation was discovered. And what happens in this plasma medium up here, which has got electrons and ions, it's mainly the electrons are involved. The electrons slow the wave down, especially at low frequencies. It turns out you're on a plot of the index of refraction as a function of frequency. You're in this part of the curve over here. High frequencies travel faster than the low frequencies. So when a lightning stroke occurs, if you're some distance away, for example, if you're clear over here in the other hemisphere, this wave tends to follow the Earth's magnetic field. You'll hear the high frequency first, then later the low frequency. It'll go dropping frequency. So when we turned the transmitter on, we were flying over a thunderstorm, and this is what you heard. Each of those whistling tones is produced by a lightning stroke. So I got involved in studying lightning strokes, and in studying whistlers, and that turned me into a physicist. Is what happened. I went from engineering to physics. In fact, there was another phenomena that we soon discovered, almost just within the first day or two. We heard these really strange things, and I'll play this one. And nobody had heard anything like this before. That's a whistler coming back from the opposite hemisphere. Did you hear it like that? Now, it turns out that frequency of that long woo, that is at the rotation frequency of protons in the magnetic field up there. And so this is kind of like a mass spectrometer, actually. On a frequency time plot here, that is, we call it a proton whistler. That asymptote there is at the proton cyclotron frequency. You can also see another one down here at the helium cyclotron frequency and so forth. So that got us into analyzing the composition of the ionosphere, which at that time was not known. This was a gift from God somehow. We had a way of analyzing what kind of ions there were up in the ionosphere. So myself and Stan Shawhan, one of my first students, I got my PhD. I did my PhD on this. It's a fairly tricky thing to explain, actually. Then we also heard others. Oh, I should have told you, proton whistlers are produced by lightning. I didn't say that, but they're produced by lightning. But we heard all kinds of other things that were not produced by lightning, and this is a good example. It's called dawn chorus. And I'll play this for you. And now we'll have an animated frequency time spectrogram here, frequency on this axis, time on this axis, and there'll be a cursor that moves along here and tells you where they are. Kind of musical signals. Now this had also been heard on the ground before we launched the spacecraft, but almost right away between Van Allen and myself, we discovered that this is a plot of the intensity of that dawn chorus as a function of distance out near the equatorial plane. And we found the peak intensity occurs right in the middle of the outer radiation belt, which is electrons. And so we immediately found out that these sounds were produced by the radiation belt. And what you're listening to is the radiation belt. Now this is a really curious thing, because if you sit in a quiet room, you do not expect the molecules over there in the corner of the room to suddenly get together with each other and somehow produce a whistling tone. But I'll guarantee you that can happen in a plasma. And a good friend of mine who I've visited with at the time, he and Charlie Kennel and Harry Petchak came up with the generation mechanism for chorus. And I'll just have to kind of abbreviate this, but what happens, an electron rotating around the magnetic field radiates a wave, and that wave lines up the phase of another electron so that it radiates exactly in phase. In other words, the two signals add, and then there's another electron after that, and that adds to it. So it's kind of a cascade effect, and this takes off and produces the whistling tone. Curiously enough, a laser is a similar phenomenon, except that's in a solid state media. This phenomena is in a plasma media. And the crucial thing that makes it go is the anisotropy. It turns out in the radiation belt out there, there's a lot more particles rotating around the magnetic field than there are going along the magnetic field, and that's what makes it go. This chorus phenomena has been found in all the magnetospheres we've visited throughout the solar system. And it plays a crucial role in the loss of radiation belt particles. Every time one of these waves is produced, it changes, we call it the pitch angle of the electron, and can cause the electron to go down and hit the atmosphere. Recently, I should ask Jolene Pickett here, you went to they just had a meeting out they're still studying this 50 years later. Jolene Pickett here went to a meeting in San Diego, and I know they're talking now about this chorus plays an important role actually in accelerating some of these electrons up to these really high energies. You're nodding your head, right? I really wanted to go to that meeting, but I have to tell you, this took priority. Now, I just had to plan this talk a little bit. Now, I'm going to talk just a little bit about auroral studies. This is a picture of sometimes called the Northern Lights. You see this up in Alaska or in Canada, but not very often. How many people have here seen the aurora over Iowa? Yeah, quite a few. It happens here. Not very often, but maybe once every few years you'll see a bright aurora. And the aurora tends to be lined up along the magnetic field line. I don't know if you've noticed that or not, but you look up there, you can some kind of send sheets like this and so forth. Now, of course, people know about the aurora since, humans first walked on Earth, at least up at high latitudes, but nobody really knew exactly how they were produced. And Engine 3 played a crucial role in that. And this is really kind of a clever deal I'm going to explain here. The spacecraft, this was Brian O'Brien. He was an assistant professor here at the time. He came up with the idea of putting a bar magnet in the spacecraft. And the bar magnet would produce a torque on the spacecraft and would line that bar magnet up along the magnetic field line. See, here's the magnetic field line of the Earth. And we did this in Engine 1, but there was a classified military satellite that did not separate from us, and we did not achieve magnetic alignment because the moment of inertia was too high. Engine 2 went in the ocean, and so Engine 3 is the first time we really got to try this out. And, okay, so everybody understand what's going on here? We have magnetic alignment. And we had a photometer, that's like a telescope, looking exactly along that axis. So as you fly over the auroral zone here, you've got a photometer looking straight down the magnetic field line, so we could then measure the light intensity right at the foot of that field line. That's really a cool approach. We had another detector, which I helped work on, called an electron multiplier. Some of the physicists in the audience will know what I'm talking about here. You take a photon multiplier and you cut the top off, then you have an electron multiplier. And so we flew that on the spacecraft, and here we are, we're going over aurora right here. You see? That's the peak auroral intensity, and here's that electron multiplier, and we see all these low energy electrons coming down producing the aurora. We also detected another type of radio emission called auroral hiss, which I won't tell you much about. It doesn't have an interesting sound. It just hisses like a snake. Here's engine 5 now. These have more and more instruments on it. I was no longer an engineer. I'm now a scientist. So I'm building instruments and not designing electronics, not the data system type thing. And on this spacecraft, I'd read a paper by Ulf Failson about making electric field measurements in space. Now, maybe I should tell you what electric fields are. If you shuffle across the floor and you touch a piece of metal and you get a spark there, that's because you got a voltage difference between your body and the metal object, and there'll be the electric field's what makes the spark. Give you another way of knowing about electric fields. If you're standing outside during a thunderstorm and your hair starts to stand up, you're about to get hit by lightning. The way we measure the electric field, we had two metal spheres here, and we measured the voltage difference between them, like with a voltmeter. Pretty straightforward. And so we could measure the electric field along this axis, like that, and we had a bar magnet in there to line it up. And Lou Frank, in our department, he was a professor from the same kind of year I was. He was involved in many of these same things I described in my early career. He had a very nice plasma analyzer, could measure the energy of the plasma. And we made two great discoveries here. Frank and Ackerson found that when you'd go through an auroral arc or over an auroral arc, the electron energy would start very low, go up to about 10 kilovolts or so, and then come down. They called that an inverted V because it's like a V upside down in an energy plot. Well, you ask, how can that be produced? Well, one way you can do it is by having an electric field along the magnetic field. We call that a parallel electric field. Now, at the time, theorists said there can't be a parallel electric field in a plasma. The reason is the electrons can move real easily along the magnetic field, and if you try to give an electric field, it makes a huge current and eliminates the electric field. But something was accelerating those electrons. And our electric field probe, we discovered at the same time, if we went across the auroral arc, the electric field that I was measuring, which is perpendicular to the B field, had a kind of S-shaped signature there. And that led me in 1972 to make this diagram of potential contours in the plasma. And that's an implication that there's a parallel electric field there that accelerates the electrons. And that's a widely reproduced figure in the literature now. Okay, I'm going to shift to a different topic now. I'm going to talk about the Earth as a radio source. Things I've been talking about so far, like dawn chorus, are all waves that are kind of confined into the magnetosphere. So what I'm going to talk about now, you can imagine, suppose you're living on Mars, and you're a graduate student, and your professor says, go find out if there's radio emissions from the Earth. That's what I'm dealing with now. Actually, we didn't go to Mars. But we had a spacecraft. This was a NASA spacecraft called IMP-6, Interplanetary Monitoring Platform. Sometimes these are kind of crazy names. But it went way out, about halfway out to the moon in an elliptical orbit. And I proposed an instrument to NASA, got funded, and we had some very long antennas, 300 feet tip-to-tip antennas on this spacecraft, metal tubes. And we launched it. It was launched. Built at Goddard Space Flight Center in Greenbelt, Maryland. And when we launched it, we saw these huge intensities on the antenna, almost a half a volt between the base of the antenna elements. You didn't need a receiver. You could have hooked a light bulb up there, and we would detect the signal. And there was a colleague of mine, Bob Stone. He had a radio astronomy instrument that was intended, and they did later measure galactic noise leveling. It was a very sensitive instrument. I always remember he called me up not too long after launch. He says, Don, I think our instrument is broke. It's completely saturated all the time. And I told him, no, our instrument, we had plenty of dynamic range, and we could measure the spectrum here, and it was almost 1 million times the kind of intensity he's trying to measure. And now this had been, just to be fair about this, the Russians had detected a kind of a similar thing up about at this frequency. Another investigator from Stanford had seen it here, but we got the whole spectrum of this thing. And It didn't take me long to discover, by comparing the radio intensities here with pictures of the aurora taken by a military satellite. There's a spacecraft that would go over the polar cap and you can take pictures of the aurora. In fact, this is the aurora here. See, the North Pole's about here, and here's the aurora. And like, for example, on this orbit here, we didn't see hardly any aurora, and there's no radio emission. Next pass here, very intense radio emission, very bright aurora. And it didn't take long to see it had something to do with the aurora. And then several of my students, Mark Bombach and Bill Kurth here, did some work on radio direction finding, and we were able to pin down the source as being along the auroral field lines at an altitude of about 5,000 kilometers, about where it's shown here. And we were able to, from the field strength, we could measure the radiated power, and it's 10 to the 9th watts. That's 1,000 megawatts. That's like a nuclear power station, just to give you the amount of power. There was another curious thing, and that is that because of the presence of the ionosphere here, that radio signal cannot get down to the ground. So here we were, and still are, living on Earth with an extremely powerful radio transmitter there in the hundreds of kilohertz region. That's kind of on the lower part of your AM, in your car radio, and the AM dials toward the lower end. And let me just put that in context. A typical radio station has 10,000 watts. That's kind of the normal number. This is 100,000 times more intense than a typical radio station. If this stuff could get through the ionosphere, we would be obliterated. We would not be able to listen to anything on your AM radio up to about 1 megahertz. So WMT and Cedar Rapids would be out of business. Then there's when we discovered this, or I published all this, very shortly there was a theorist, Wu and Lee, Ching Wu, came out here, and we discussed all this in connection with the aurora. And he was a good theorist. I'm not a full-blooded theorist, and he came up with a mechanism that's called the cyclotron maser, and that is now believed to be the origin of this. 1% of the energy in the aurora goes into this radio emission. I'll talk a little more about it. And not only that, it's kind of like the chorus. It's a coherent mechanism. The electrons get together and they just produce this. And I'm going to play up there in the top, right here, I'm going to play the sounds of the aurora. This is actually up at 250 to 260 megahertz. You can't hear at that frequency, so we've translated it down so you can hear it just like with a radio. And down at the bottom, just for motivation, I'll show you a video of aurora. Unfortunately, this aurora has nothing to do with that radio emission up there. I'm just trying to motivate, let's see. But you'll see that radio emission is highly dynamic, and so is the aurora. So here we go. So if you're a graduate student living on Mars, studying the Earth, that's what you'd hear in your radio receiver. Now I'm going to switch topics to the essentially last topic I'm going to talk about, and that is the missions to the outer planets. The outer planets are Jupiter, Saturn, Uranus, and Neptune, and they're a long ways away, and they're very hard to get to. And our laboratory has had 4 missions to the outer planets. Actually, I should count them. There's actually 2 spacecraft here, Pioneer 10 and 11, Voyager 1 and 2, then Galileo and Cassini. Now, it was known that Jupiter had a radiation belt. The reason we knew that is you can detect radio emissions from Jupiter. You can detect that on the ground. In fact, you take a simple antenna and put it outside here and listen at 20 to 30 megahertz, you can pick up Jupiter. So it was known about the time the Van Allen radiation belt was discovered that Jupiter probably had a radiation belt. And so these were all NASA missions, and I proposed for Pioneer 10 and 11, but I did not succeed. Van Allen proposed. In fact, he was one of the persons that really proposed this mission, got it underway, and then when he proposed to NASA to get funded for it, he succeeded. And part of the reason for that was because they knew it had a radiation belt, they put essentially only instruments on that were directed toward understanding this radiation belt at Jupiter. That was one of Van Allen's favorite projects, I would have to say, because he made the first measurements of the radiation belt at Jupiter. And then actually Pioneer 11, through an interesting trick of orbital mechanics, they were able to get that spacecraft also to Saturn. Now, however, these other three, we are all selected to build radio instruments. In fact, you can see our antenna. That's our antenna there. Can't see it on this. This is the bay of the shuttle when they're launching. I can't see our antenna there, but Cassini, which is in orbit around Saturn right now, you can see our rather long antenna there. Let me talk about Voyager 1 and 2. Now, Marie tells me never to show these orbital slides, but I just have to do it. This is called the Grand Tour. And the reason is that the planets Jupiter, Saturn, Uranus, and Neptune in the year 1977 were lined up in just the perfect way that you could launch from Earth and go by all four of these planets. And that was called the Grand Tour. By the way, the mission was proposed to Congress as the Grand Tour, but Congress decided the cost was too high, and so they canceled the mission. So JPL came back and says, okay, we're going to call it the Mariner Jupiter-Saturn mission, and stop the costing at Saturn. That was funded, but of course the planets were still in the same way, so when we got to Saturn, we just renamed the mission the Uranus-Neptune mission and went on our way, of course with more money. Now you'll notice that Voyager 1 here did not go to Uranus and Neptune. The reason is Carl Sagan wanted to fly by the moon Titan here. And it was known that Titan had an atmosphere at the time, and he thought there might be a greenhouse effect there, a place that would be comfortable for life. And so we made that choice, and if we go to Titan, we can't go to Uranus. That's the reason for it. We did succeed in making the entire flight out to Neptune with Voyager 2. And you can look in, you can get on the World Wide Web, and you can pick up an astronomy book. Incidentally, what are the merits of NASA missions? Well, half of an astronomy book is stuff that came out of space research, including our knowledge that we're sort of alone in the solar system. You know, we used to think there were living things on Venus, maybe on Mars. Well, forget it. It's not even sure there's any other living thing in the universe except that in the solar system other than Earth. Anyway, here's Jupiter. Huge object, big ball of gas. Here's the moon Io in orbit around Jupiter. It's not nearly that big. It's almost a dot compared to Jupiter. I've blown it up so you can see it. All these black dots are volcanoes. Most volcanic object in the solar system. Saturn, of course, even my young grandkids knew at an early age, Saturn, it had the rings. I guess Carl's not here, is he? Uranus, Neptune. Here's a moon at Neptune called Triton. It's got some curious black features that are thought to be some kind of geysers or volcanoes or something. Now, I'll just kind of touch on a few things that our group discovered at Jupiter. As we flew by Jupiter, we detected whistlers. And I ought to give you a test. What is whistler? If you hear a whistler, what does it mean? Lightning. Right. Well, I guess you could read it up there. And here is the limb of the planet. I'm going to play the sound recording. You listen carefully, and you can hear the whistlers. They last longer because Jupiter's huge, and it takes a long time for the signal to get out there. And so we discovered lightning on Jupiter. That's the first planet other than Earth that is now known to have lightning. After we recorded these whistlers, the imaging people, when we went around in the backside of the planet, they took pictures looking toward the atmosphere, and they could see lightning flashes in the atmosphere. These are now called superbolts. And the reason they're called super bolts is the distance from here to here to the two edges is about like from the east coast of the United States to the west coast. So can you envision a lightning flash that is like across the whole country? These things are just extremely intense. I hope I explained that's the limb of the planet you're on, looking on the back side. Now, we also detected, this is a picture of the radiation belt. It turns out even ground-based antennas can, from the radio emission produced by these energetic electrons in its radiation belt, you can take a picture of the radiation belt of Jupiter. But when we went in there and flew through that radiation belt, we detected dawn chorus. I hope you can detect the similarity. Frequency is a little different. In fact, I had to play it at half speed so you could hear it clearly. But same rising tones and so forth. So this is the radiation belt that Jupiter is singing to you. And we've detected dawn chorus at Uranus and Neptune, but and at Saturn, Uranus, and Neptune. I will not show that data, though, because we just don't have enough time. Another thing we did with the Voyager is we made measurements, detected radio emissions from all of these planets. And now Jupiter, we knew the frequency, there's 10 megahertz. We knew about Jupiter, right at the beginning of the space age, but we knew nothing about these others. And we now know that this mechanism called the cyclotron maser operates at all the planets, all these magnetized planets. And they play an important role in astronomy books, because in case you ever wondered what the rotation rate of these planets is, you can look it up on the back of the book. For example, Jupiter is 9 hours, 55 minutes, 29.7 seconds. Well, Jupiter is covered with clouds, and the clouds are moving at different rates at different latitudes, and there's no solid surface. So how can you get the rotation rate? Well, we get it from the radio emission. The radio emission is controlled by the magnetic field, and the magnetic field links to the deep interior of the planet. And as the planet rotates here, the magnetic dipole axis of the planet is typically tipped a little bit, about 9 degrees if I remember right at Jupiter. And as it rotates, the radio beam of the radiation coming out from the planet kind of wobbles. And if you're out here with a spacecraft, you can detect the modulation, and all you do is do that over a few years and you get a really accurate period. So that's been done at all these planets, outer planets. Now I'm going to switch to the Voyager interstellar mission. After we arrived at Neptune, well, that's where the funding ended. So what did NASA do? It turns out we're on an escape trajectory from the sun. With Voyager 1, we're moving out at about 3 astronomical units, 3.5 astronomical units per year. Astronomical units, the distance from the sun to the Earth. And so NASA funded us for the interstellar mission. And we're still getting data. It was launched in 1977. This is 2009. So that's 32 years we've been flying with both Voyager 1 and Voyager 2, and we're still getting data. And we're out here about this far away. We're at 109 astronomical units with Voyager 1. Let me put that in a perspective. It takes 8 minutes for a radio wave to go from the sun to the Earth. Or let me put it differently. When the astronauts landed on the moon, you could perceive the time delay when mission control would talk to them and they would answer back. It's about 2 seconds, I think. It takes now 14 hours for the radio signal to come back from the spacecraft to the Earth. Astronomers like to measure distances in light years. You've probably heard of light years. Light moves really fast, right? And a light year is the distance light moves in 1 year. We're not out there at a light year yet, but we're getting close to a light day. And we're still getting data. Now, why in heaven's name would the public fund such an enterprise? The reason is we are trying to penetrate into the interstellar medium. And, well, why aren't we there yet? The reason is the solar wind blowing out from the sun here kind of pushes the interstellar medium away. Another factor is it turns out the sun is moving this way at a speed relative to the nearby stars of about 26 kilometers per second. This means the sun is sort of plowing through this interstellar gas, and so the interstellar gas goes around the region dominated by the solar wind. That boundary is called the heliopause. We have not got there yet, even after 32 years. It's a theoretical boundary. We're pretty sure it's there, but the idea eventually is to make our way into the pristine interstellar medium out here. Now, there may or may not be a bow shock out here. We don't actually know whether the sun's moving fast enough. It depends on the temperature of the interstellar medium and so forth. So that's what we're up to right now. Now, okay, how are we doing? Well, a few years ago, quite a few years ago, this is a plot that goes from 1982 here up to, I guess I ran it up to 2004. We have even more data here. Back in 1983-84, Bill Kurth over here, I ought to have you put up your hand, Bill. You paying attention there? Bill discovered this radio emission. At the time, we didn't know what it was. There was some suspicion it was coming from Jupiter, maybe. We just didn't know. And time went on, and about 11 years later, we saw another, even more intense radio emission here. During this event, we started putting pieces together, and the top plot is a cosmic ray intensity plot at Earth. Now, these abrupt spikes downward are when there is a big solar flare at the sun. That sends a shock wave out that kind of pushes the cosmic rays away, decreases their intensity. That's what's happening here. So that's really evidence of a very strong shock propagating out through the solar system. And you'll notice here that this event occurred 412 days after that. That's the biggest event